We're not going to do all of these notes as video notes, but this will buy us some time in class, and this will also give you the whole period today to take the test. So I'm just going to probably do the first two examples depending on how time goes, and because we also need to address the SHRATEY steps that you're going to get on your reference handout with these notes. So what the SHRATEY steps do is, a lot of people think SHRATEY is a process for graphing rational functions. What you're about to find out the hard way, unfortunately, is that SHRATEY will almost never generate a rational graph. It generates specific characteristics of a rational graph. And so SHRATEY is actually a process for analyzing rational equations, not graphing them. Okay, so what the first step of SHRATEY, your reference handout should tell you, it says to simplify the equation. What that means is you're going to factor and reduce whenever you can. Okay, so on example 1 right here, what you would put is you would put none, or you would simply just rewrite the original equation, because this equation right here doesn't factor and reduce. So then what the next step of SHRATEY tells you to do is to locate holes. So you've done holes a couple of times. You did holes in Algebra 2. That's what your Algebra 2 teachers referred to as removable discontinuities. You also did holes at the beginning of this year when we were in our limits unit. Anytime we got 0 over 0, we had what we called indeterminate form, and that meant that there was a hole in the graph. So what happens is a hole occurs when a vertical asymptote cancels out of an equation. Okay, so it only occurs when the equation can be simplified. So in this case, if your equation can't be simplified, then you have no holes. Okay, so this rational function can't be simplified, so it has no holes. So then if you look at your reference handout again, the next step is R, and that's to locate the roots of your equation. And what it says, it actually says it on the reference handout. It says take your numerator and set it equal to 0 and solve it. So in this case, you would have one root, and it would be at x equals 0. Then the next step on your reference handout says to do it says you're locating asymptotes. It more specifically means you're locating vertical asymptotes. And what it says on that reference handout is take your denominator and set it equal to 0. So in the case of example 1, if I took that denominator and set it equal to 0, I would get x equals 3/2. You need to make really sure that when it comes to the A step, and actually the E step, which we'll get to in a second, you need to write it as an equation. This is a vertical line. It's got to be drawn as a dashed line, and it's a line that your graph will never cross. Okay, this one doesn't have to be written as an equation. It can be written as an equation. It could be written as coordinates. That one is just a point. It's just your x-intercept, so that one's not a big deal. Okay, the T step is what we call a special behavior step. If you look at your reference handout, what it wants you to do is look at the numerator and denominator and decide if you have any squared factors. So example, if I had an x squared over x plus 3, then I have a factor that's squared on top. Okay, if I flipped that, if I had x plus 3 over x squared, then I would have what they call a special squared factor on bottom. And not a lot of these deal with them. We're going to see it here in a couple of examples, but probably not on tonight's video notes. So this one doesn't even have anything that's squared in this equation, so we certainly don't have any factors that are squared in this equation. So there's no special behavior. So we'll practice that and talk more about it when we actually get to a problem that has that. The E step is end behavior, and we've done end behavior. Okay, now remember, end behavior is talking about the limit as x approaches infinity. You're talking about what does the right edge and the left edge of this graph do. Well, on rational functions, the left edge and the right edge do the same thing. Okay, so you only need to worry about one. And we've done these types of problems before. We did them in the limits unit. We did them in the sequences and series unit, actually. So if I wanted to know what the limit as x approached infinity of this rational function was, then remember what we talked about is that you would take the leading term on top and the leading term on bottom, and you would reduce, and you would see what you ended up with. In this case, when you reduce, the x's outright cancel, and 4 divided by 2 is 2. And so what that tells me is that my end behavior approaches a y value of 2, which means I've got a horizontal asymptote there. So the E step is always going to be calculating a horizontal asymptote, or what we call an oblique asymptote. The horizontals are the only ones you've seen so far. So obliques will be new, and we'll deal with them when we get to them. Okay? And then the y-intercept is, of course, the same as it is for every other equation. It's what you get when you plug 0 in to the equation. So when I plug 0 in to this equation, I get 0 over negative 3, which is 0. So my y-intercept is 0. Okay? Now, what I'm about to show you is the reason why SHRATEY will not graph rational functions. So there's extra stuff that you will always have to do in this unit. Okay? I'm going to erase this part right here just to give my graph a little bit of room. So think about all the stuff we know about our graph. We know 2, 3, 4, 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4. Okay. We know that we have an x-intercept at 0, so I'm going to hit my axis right there. We know that we have a vertical asymptote at x equals 1.5. So I draw a vertical dashed line right down there. We know we have a horizontal asymptote. That's our end behavior, very important. Only controls the edges of my graph, but it exists at y equals 2. So I'm going to go ahead and draw that in right there. And then my y-intercept is one I've already got on there. That's it. That's all I know about my graph. I don't know any other points on my graph. So this graph is going to be something that looks like this. I'm going to need 2 branches to that graph. And so in order to actually generate the graph, you're still going to have to do a table of values. That's why SHRATEY is not a graphing process. Okay, it is an analysis process. So the general rule is you need 3 points on every branch. So I've got this point over here. I'm going to need 2 more points on that. Now what I want to do is I want to choose the x value immediately to the left of that vertical asymptote. So I'm going to do x equals 1. And then I want to choose an x value way down here towards the left end of my graph so that I can see how quickly my graph flattens out. So I'm going to choose something like negative 1, 2, 3, 4, 5. I guess I'm going to go all the way down to negative 6, as far as I can towards the edge of my graph. Okay, that'll give me 2 more points on my left branch. So when I plug 1 into my equation, I get a 4 on top, and I get negative 1, or no, yeah, negative 1 on bottom, and so I get negative 4. So when x is 1, I get 1, 2, 3, negative 4. There's a point right there. And then when I plug in negative 6, I get negative 24 on top, and then I get negative 12 minus 3, which is negative 15 on bottom. So number 1 is going to be positive. And then it's 1 and 9/15. Now the reason I wrote it like that is because 9/15 is just a little bit bigger than a half. Okay, and we can talk more about how I know that kind of estimated value in class. But that's a little bit more than 1.5. So way down here at negative 6, I'm somewhere right around here, a little bit more than 1.5. And so that gives me very good shape to my graph. I know I'm going to curve to follow that vertical asymptote. I'm going to curve to follow that horizontal asymptote at the edge. There's my left branch. Now I need 3 x values for the right branch. So here's my vertical asymptote. I'm going to choose the number immediately to the right of it. I'm going to choose 2. I'm going to choose another one just a little bit farther down, maybe like 4. And then I'm going to choose one as close to the edge as I can get it, so like 6. Okay, so when I plug 2 into this equation, I get 8 on top, and I get 4 minus 3, so 1 on bottom, so I get a y value of 8. So 1, 2, 3, 4, 8 would be somewhere right around here. Then when I plug in a 4, I get 16 on top, and I get 8 minus 3, which is 5 on bottom. So I get 3 and a fifth. So at 1, 2, 3, 4, I'm at 1, 2, 3 and a fifth, so just above 3. And then last but not least, I try 6, and I get 24 on top, and I get 12 minus 3, which is 9 on bottom, and I get 2 and 6/9, which is 2/3. And so way down here at 1, 2, 3, 4, 5, 6, I'm at 2 and 2/3. And so I can see it beginning to curve and flatten out. So I can then draw the right branch. Okay? So first of all, never leave any of these steps empty. You always want to write none or NA or something for the steps that don't apply. But even after you've done all of the analysis steps, you need to generate a table to draw the graph. And it will be part of the rubric when you do eventually take a test on this. Okay, so we'll try one more example, just one. That's it. Okay, this equation doesn't simplify. It's already factored and nothing cancels, which means there are no holes again, just like before. When I take my numerator and I set it equal to 0, I have two different factors up there. And so I get two x-intercepts. I get x equals -1, and I get x equals 6. So there's my two x-intercepts. And then I take my denominator, which is x minus 2. I can include the squared, but it's not going to change anything. And I set it equal to 0. And so I'm going to have a vertical asymptote at x equals 2, and that one's got to be written as an equation. Okay? Now this time, I do have a squared factor in the denominator. Okay? I have x minus 2 being squared in the denominator. So if you look at your reference handout, it says that when you have a special squared factor in the denominator, your branches will move together at the asymptote. So what that's telling you is that either both branches are going to head down the asymptote or both are going to head up. So we'll see which one ours does, but let's say what I know about my graph is that either both branches are going to do this and head down that vertical asymptote, or both branches are going to do that and head up it. You won't know until you actually generate the table and some other information. Okay. The end behavior, the leading term on top would be an x squared if I FOILed it out, which I very rarely do. And the leading term on bottom would also be an x squared. And so that reduces down to 1. So I'm going to have a horizontal asymptote at y equals 1. Okay, and then my y-intercept, when I plug 0 into the equation, I'm going to come up here to show the work. My first factor would be 0 plus 1. My second factor would be 0 minus 6. And my denominator would be -2 squared. So I would have -6 over 4, which is -3/2. Okay, now this one, you actually have more points on your graph. So I'm going to try to scale smaller, which is very hard to do with a stylus on an iPad, but and then you guys are going to practice this. Okay, so I've got an x-intercept at -1. Put that point on the graph. I've got an x-intercept at 6. 1, 2, 3, 4, 5, 6. I've got a vertical asymptote at 2. So right there. I've got a horizontal asymptote at y equals 1, and keep in mind that will only control the ends of the graph. My graph does not control, it's not controlled in the middle. And then I've got a y-intercept at -1.5, so right there. So I know 3 points on my graph. Okay, and so what I want you guys to do, I want you to pause. I want you to do a table. You only need one more point on the left branch, and I would recommend you plug in x equals 1 because that's immediately straddling that vertical asymptote. That'll give you the last point for the left branch, and then you only need 2 points for the right branch. So I'm going to say that you should do this x value as well, which is 3, and then choose one much farther down so that you can see what your right end looks like. So something like 9. Okay, so pause it. Do those 3 number crunches in the table and see what your sketch looks like. Okay, so if you number crunched correctly, this is what your graph would now look like. And you see how both branches do actually move down the vertical asymptote, which agrees with that t-step. Okay, so we'll practice more of this in class. This just gets us started and gives us more time in class to do more problems and get help. Okay.